Okay, make sure you're following the last can. Don't buy chronological order in the left. Go by this way. Okay. And there's some dry labs coming up. Well, anyway, make sure you follow this. Okay. Perfect. Saturday. Bad part about doing video. Yes. All right, any questions about things? Now, I have a question, regarding, lab time to start. The lab starts after lecture. The lecture goes to 10 minutes, that means lab starts 10 minutes later, or break down. Lab goes for 2 hours, lab starts 2 minutes after that. Okay? So don't go by the 140 time slot. But sometimes it'll work, but usually it won't. And today we're going to start into we're going to be doing quantities of chemical reactions. Okay, so the lecture schedule, okay, so it's going to be Matthew again. Unit 2 and Unit 3 will repeat are very, very important as far as preparatory for units. Remember the purpose of this class. So this unit, the next one is going to be mapping, and but they're extremely important. So today, I'm going to called very important unit in chemistry is called mole and that is going to be pervasive throughout the whole semester. Everything's related to the mole in chemistry and physics and engineering. The other thing we're going to talk about in this unit is something called balancing react. Up to now, we have an reactants, chemical reactions. I'm going to show you what that's like and how to do it. All right. Without any more questions, let's go ahead and get started. And this file here is under modules and files both. Okay, so the fancy name for what we're going to be doing in Unit 2 and mostly Unit 3 or something called stoichiometry. Stoichiometry is the quantitative relationship between the reactants and products. In fact, a funny story, I was, this was, I don't know, about 12, 15 years ago. I was on a test and a very similar class as this, and I needed 5 points. I wanted to bring it up to 100 points. So and the test was on stoichiometry. So the question was, what is the test about? I mean, I thought everyone would get 5 points, right? About a third of the class missed that question. It was like, kidding me? Just look on the first page of the test, it says stoichiometry test. Anyway, okay. So this is a typical stoichiometric problem. Okay, we've got with combustion of methane, which is CH4, and the combustion of methane in oxygen to carbon dioxide and water. How many grams of water are produced
of 15 grams of, if 15 grams of methane are consumed. So remember the 4 steps of problem solving. Step 1 is balance the reaction equation. We always skip that because we never had a chemical reaction. Well, unit 2, you're gonna have lots of chemical reactions. The second step is what's given. The third step is what are you trying to calculate? And then the fourth step is a setup. So the main difference is that first number 1 is the chemical reaction. Now, I'm not going to solve this right now because we haven't talked about balancing the chemical equation yet. But this is what the problems in this unit are going to look like. Very similar to this one. Okay, so we need to have a couple more definitions. And I mentioned the unit called mole. Now, the word mole comes from the word molecule. And what it is, it's a very convenient unit because in chemistry, physics, and engineering, atoms are really small. Now, yesterday I mentioned how small they were. And I also mentioned that decimal number on the periodic table. So, the mole is defined as 6 times 6.02 times 10 to the 23rd atoms or molecules. That's how small these atoms are. Really small. So in 1 mole of anything, there are that many atoms or molecules. Now that's just a counting number. So when you read a problem and it says, how many atoms of hydrogen are there, something like that, how many? That's your key to use this number here, 602 times 10 to the 23rd. Okay, so if we go back to the periodic table from yesterday and look at carbon, the 2 numbers on the periodic table, the top one is how many protons, you remember. It's also called the atomic number. Now the 1201, I mentioned that's measured in atomic AMU, atomic mass units. However, the other thing I mentioned that number represents is something called the it's also called the molar mass of carbon. Sometimes it's referred to as atomic mass. So what is the molar mass then? So we have this definition of a mole. And what it is grams in 1 mole. So if I took 6.02 times 10 to the 23rd atoms of carbon and weighed it, it would weigh 1201 grams. So for unit 2, your first conversion factor, now all conversion factors, of course, have got the inverse. Now that's specific to the compound you're talking about. So moles of water, grams of a molar mass for water is different than the molar mass for carbon dioxide because the atoms are different. Different atoms have different molar masses. Second conversion factor. Okay, so 6.02 times 10 to the 23rd molecules or atoms per mole. And then, of course, the inverse is true. Now that's non-chemical specific. So it doesn't matter if it's water or carbon dioxide, it's still 602 times 10 to the 23rd. Molar mass, though, is very, very specific. So remember that when we're counting how many, these are the key words you key into. And the last one, there's one more, has to do with gases. So for gases, it's 22.4 liters per mole at standard temperature pressure. If it's not at standard temperature and pressure, it's not 22.4. Now, when you get to unit 4, we're going to talk about gases much more specifically. But for right now, anytime we talk about gases, it will always be at standard temperature and pressure. Okay, so those are the conversion factors. And this is non-specific as well, gases. So it's any gas. It could be uranium, hexafluoride, or water gas. Still, it's 22.4 liters per mole. And of course, the inverse is always true. So that's also non-chemical specific. So the only one that's specific is the molar mass. Okay, so let's look at a typical problem involving some of these conversion factors. I think I have some already. Now, whenever we're doing these problems in unit 2 and unit 3, you have to have your periodic table out. Okay, so how many moles are in 2.34 grams of water? Okay, so what's given? $234, right. Okay, and what are we trying to calculate? Moles. This is just like unit 1 now. Same process. Okay, so do we have a conversion factor that's got grams and moles in it? Yes. We've got the molar mass. Our grams are going to cancel. So we have to figure the molar mass for water. So using our periodic table, okay, this is an interesting one. I'm going to put another one on here. This is one from 1A. Okay, so we look at the periodic table, the one for our class. Okay, we can see hydrogen is 1.01. And oxygen is 16.00. So that's what we need to figure out the molar mass for water is we take the constituent atoms, hydrogen and oxygen, to find the molar mass for each one. Then we add them together. Now, all these molar masses on this periodic table we're using are already rounded to 2 decimal places. Okay, so for water, we have 2 hydrogens, 1 oxygen. Each hydrogen, the molar mass is 101. For oxygen, it's 16. Okay, so that gives us 1802 grams per mole. Okay, so grams cancel, leaves us with moles. And how many sig figs is the answer going to have? How many sig figs is the answer going to have? 3, right? So 0.130 moles. Now, now for unit 2, this is as simple as it gets. A one stepper. Normally, for stoichiometric problems, normally there are 3 conversions you're going to be doing. And one of them comes from the balanced equation. Okay, how many grams are in 12.45 moles of water? We're starting with so we want the the given to cancel. And we already calculated the molar mass for water is 1802. And that's it. Okay, 4 sig figs, 4 sig figs. The answer is going to have 4 sig figs. Yeah. No, again, on scientific notation for my class, if you're comfortable with a number, in other words, it's not awkward for you, leave it. If you think it's kind of too big or too small, then go to scientific notation. And notice 6.02 times 10 to the 23rd. That's 21 zeros. So is that awkward for you? Same thing, yeah.
Just for well, that
If we're,
not
we're counting, if we counting, in other words, how many atoms are in 12.01 grams of carbon? 6.02 times 10 to the 23rd.
so one.
1 mole of atoms is, so if we took 602 times 10 to the 23rd and weighed them of carbon, it would weigh 12 grams. And that's by definition 1 mole. How can I re-explain this? I can see you're not getting it. You have that look.
And the meter conference.
Correct. Just like dozen,
Yeah. So what does
12, right? I'm sorry, say again?
Earlier, we ran it down.
Ah. It's a good question. Okay, so what does 1 atom mean weigh mass wise? Oh, it's easy. If I said we have 12 apples, how would we figure out what 1 would weigh? We divide by 12 because that's how many are in the bunch. In the case of atoms, it's going to be in the bunch 602 times 10 to the 23rd. So we divide 12 by 602 times 10 to the 23rd. And that's what 1 carbon atom will weigh. Let's do it right now. Okay. So we know how many 602 times 10 to the 23rd weigh. That weighs 12 grams, right? Okay, so I'm going to take 12 grams Let's go 1201 grams. And now we're going to divide that by just like 10 apples, we have to divide by 10. A mole, we have to divide by 602 times 10 to the 23rd. Now, this is going to be a really tiny number. See how tiny that is? So that's what one carbon atom weighs. If we had a super duper weighing scale, we put that one atom, that's what it would show. Does that make sense, that calculation? It's analogous to the apples,
So what is one?
12.01 grams.
There.
Okay, just like if we had we had a dozen apples, weighs 5 pounds. What does one weigh? You divide the 5 pounds by 12, right? Same thing. If a mole weighs 1201 grams, what does one weigh? We divide by how many are in that mole? 602 times 10 to the 23rd. Okay, good. All right. Text me later if this is still unclear, okay? Okay. Let's go through these sample questions here. How many liters of water gas is in 2.34 grams of water? Notice I put the H2O above the 2.34. The reason I do that is because when we get to a reaction, you need to know what chemicals correspond to what numbers. So the 234 corresponds to water. We'll put that up there above. Okay, so now we're talking about gas now, and this would be at STP. So do we have a conversion factor for grams and liter? We have liters and moles and grams and moles. So what's the common unit here? Moles. So first convert to moles. Then for moles, we're going to go to liters. Now liters are uppercase L. Milliliters is little m, big L. Now that's the first two-step problem we have. So if in doubt, convert to moles. If in doubt, convert to moles, because it's a universal unit. Everything relates to moles. So if in doubt, convert to moles and then go from there. Think of it as like a spoke on a wheel. You always go through the spoke, the wheel hub, which is going to be moles. Okay, let's do another one. How many molecules of water are in 3.45 liters at STP of water? So as we mentioned liters in unit 2 and 3, we're talking about, excuse me, in unit 2. In unit 3, there's going to be a different kind of liter. So if we're talking about gaseous liters, we've got a conversion factor for that. So what's given? 345 liters of gas. And I specified water, but I didn't need to, because with gas, it doesn't matter the chemical. Also, when we're talking about how many molecules, that's non-specific also. So I can replace water with gasoline. I can replace with anything because it's non-specific. Because all we're doing is counting. So first thing we need to do, there's no direct correlation between counting and liters, but if we go through moles, there is a correlation. So first step is convert to moles, cancel the given, just like unit 1. Now we have moles. Now we're going to go to how many. So moles cancel with number of molecules. Okay. Now the 22.4 liters is not defined. So that's 3 sig figs. Same with the 602. 3 sig figs on that. So we have 3, 3, 3. So our answer is 3 sig figs. You guys okay with these? All right. Now this is a little trickier, this question here. How many atoms of hydrogen are in 3.45 liters of water? Yeah,
Just going back on that other question, got 9.27. Times 10 to the 24.
um. My calculation, I'd have to look at the numbers you put in. Okay. All right, so we're starting with 345. liters of water. Now, what's the formula for water? H2O. Okay, so let me give you another example. If we have 10 bicycles, how many wheels do we have? Hmm?
20.
How did you get 20?
Unless they're like bicycles, they have two wheels.
Right, so you have a conversion factor of 2 wheels per bike. Right? Okay, so if we do that, so we have 10 bikes. In our normal fashion here, okay, bikes cancel. These are the wheels, so 2 times 10 is 20 wheels. And we're gonna play the same game with water. If I have 10 waters, it's 2 5s. If I have 10 waters, how many hydrogens do I have? 20. 20, as each hydrogen has 2 hydrogens. Okay,
Let's put it that way, then. Lots, paints a lot clearer.
the bicycle. See, everyone's very comfortable with that bicycle thing. But when it comes to atoms in a molecule. All right, so we got to keep that in mind. That's how we go from molecules of water to hydrogen. It's a 2-to-1 ratio. So first thing we need to do is calculate moles. Next, we need to calculate molecules of water. Now we need to throw in our atoms of hydrogen per 1 molecule. Molecules cancel, leaves us with atoms. Okay, yeah. It's 20,
Oh,
2 H's. H looks. It's an H, not a 4. That was your question, right? Okay, sorry. Not the first time someone's confused my bad handwriting. Okay, does everyone understand the setup? If in doubt, convert to moles. Okay, we're using our 22.4 liter conversion to get to moles. And for moles, we need to figure out how many molecules of water. And then we use the 602 times 10 to the 23rd. And then we convert from molecules to atoms. Okay, so let's see what the answer is here. So unless you do the 2-to-1 ratio, you're gonna end up with the answer you're gonna end up with is molecules of water, not atoms of hydrogen. Okay, so those are some examples of problems where there's no chemical reaction. So there's no step one equation to balance. So that's what I wanted to cover today. The next thing we're gonna do is we're gonna look at chemical equations. Then we're gonna put chemical equations with what we did today together. Which is how to answer this question here. Because right now, this equation is saying the given is methane, CH4, and we want to calculate water. So what's going to glue those together is the chemical equation, the reaction equation. Okay, so that's it for today. We're going to start lab early today. And now on this lab, it's a wet lab. You're going to need goggles, appropriate shoes, and a lab coat. I have goggles to loan if you haven't got your goggles yet. Okay, I'm gonna wait, and your corrections on your test, by the way, are due Tuesday. I need to see if there's an assignment there. If not, I'm not great one. Okay, so what you're gonna do, you're gonna take your old test and correct it. And then scan that.